All right, here's your notes on section 4.2, Newton's law of universal gravitation. Okay, so Newton's law, we talked about, we talked about the force due to gravity um, in the first topic here, where we said Fg is proportional to 1 over r squared, again, different radius, and basically that every time you move one radius away, it, it actually it goes down by 1 over r squared. So like 2r is equal to 1 quarter Fg. 3r would be 1/9 Fg, and so on. And so Newton's law of universal gravitation is any two objects, A and B, in the universe exert gravitational forces of equal magnitude but opposite direction on each other. Okay, the forces are directed along the line joining the centers of both objects. The magnitude of the gravitational force is given by this formula here. So this is Newton's law of universal gravitation. Fg is equal to G, capital G, make sure that this is different than lowercase g, A times the mass of A times the mass of B divided by r squared. And so we'll go through what each of these are. So Fg, gravitational force measured in newtons. Okay, we've done that before. Again, M, mass of object A, B, mass of object B, okay, and R is the distance between the two centers of two objects. And so that's where if you're sitting next to someone, okay, there is gravitational force between the two of you. Okay, it's not very much. Your Fg is going to be really small, and what makes it really small is partially how our distance is squared, but then also our um, capital G, which is, whoops, back here, the universal gravitational constant, which is in your data on your formula sheet, okay, and it's 6.67 times 10 to the negative 11 newtons times meters squared divided by kilograms squared. Okay, looking at some different problems. Okay, so we have two different masses that are separated by a distance. Okay, so the magnitude of force for these two would be Fg. Okay, if we change the size of any of our masses, we're going to change our gravitational force. Okay, so if we double the mass, because force is proportional to mass, if we double one of the masses, we're going to double the force. Okay, again, if we change these masses, because the force of gravity is proportional, directly proportional, we just have to times these two together. So 2 times 3, they're going to have these arrows here showing the vector force, like a force between the two. So they'll have 6 times the force, so these vectors are going to be a lot bigger than these other ones. Okay. If we half the distance, again, because Fg is uh, it's indirectly, or it's um, indirectly proportional to d, okay, or to r, okay, 1 over r squared. Okay, if we half of it, so 1 over 1/2 squared, which is equal to 1 over 0.25, which is equal to 4. And so, again, they would have the vector lines that are between our 2 and our 6 for length. Okay, if we double the distance, again, we get 1/4 because it's 1 over r squared. So 1 over 2 squared, 2 squared is 4, so 1 over 4 is our Fg. And then if we double the distance, okay, and then we have 2 times the mass here, 3 times the mass here, basically 2 times 3 is 6, that's what's on top, and then 2 over 2 squared, which is 4. So we got 6/4 or 3/2, either way. Okay, and how they, this universal, basically capital G, determine the value of universal gravitational constant, which is capital G. Okay, this Newton kind of came up with this, but had no way to measure it. Okay, that Henry Cavendish was able to measure this later using a torsion balance. So he has these two different masses here, one larger mass, one smaller mass. Okay, this is our torsion fiber, so it can torque, which means to twist just a small amount. Okay, we have a mirror here, a laser, and then some sort of screen to show the deflection. Okay, and so by knowing like how far our deflection point is and what these two masses are, we can use that to then discover our gravitational constant. Okay, so this is kind of what happened. So we have these forces Fg between the two masses. Okay, they're equal. Okay, using the formula Fg equals capital G times mass of one, mass of the other over r squared. Okay, by getting the r by the amount that the mirror is showing the laser, how far it's pushed over. Okay, then we can find r. So rearrange that formula to solve for g. Okay, then we can just put our numbers in there. And so that's something you're asked to do on your assignment. So this is the rearranged formula. Okay, and then you have to find the percent error. Okay, make sure like the formula is given, just put those numbers in, yeah, as I said. Okay, remember for percent error, we want the absolute value, like we don't need any negative numbers. Okay, another example here showing kind of the different, it's showing like for our force due to gravity at different points. Okay, so just comparing the two. Okay, this is in your textbook. Okay, on page 206. So you can go through and kind of see how that is solved. Basically, you know big G, you know the mass of the person, mass of the Earth, and then the radius. Okay, you have to add, so like for this one, like the radius would be of the radius of the Earth. Okay, for this, now you have to add the height of Mount Logan to get that second radius. Okay, again, it's all shown to you in your textbook on page 206 and 207. Okay, another example, okay, you can also use proportionalities to solve gravitational problems. There's a lot of questions on this in your on your assignment. Okay, and so just if you have the FG for a certain radius, okay, if you double the radius, okay, again, the masses don't, or actually the masses are changing, but it looks like they're just doing the opposite. So yeah, our masses, it explains in the textbook on page 208, but yeah, it says in the textbook, our masses are increasing by 6 times, or mass A is 6 times bigger, mass B is halved. Okay, and so to get kind of the masses, okay, you'd have to go 6 times 1/2, so you get the change is 3m, and then for your radius, because it's doubled, you get 1 over r squared once you double the 2, so you get 1 over 4. So then you get overall, you're going to change by a factor of 3 over 4, and you should end, like, then you just times it by your original number. Okay, using superposition to find the net gravitational force on the Earth. So again, this is in your textbook on page 209, shows you how to solve these problems. Again, you can go through that on that page. Okay, make sure for any of these, it helps to draw a free body diagram and realize like they're going in different directions. Okay, and so you have to have one negative, one positive, however you want to do that. Okay, and just, yeah, this is the next example. Okay, showing, this is on page 212. You can go through that. Just gotta pause this here for a second. All right. Oh, we skipped the slide ahead. Okay, but you can go over that example. Last thing is just talking about gravitational assist. So when we send out different satellites, okay, to like Voyager 2, Voyager 1, okay, what we do is like when they're calculating, we send them past certain planets in order to use their gravitational pull as it kind of rotates around. It'll accelerate, okay, our satellite in order to send it to a distant planet. Okay, and so again, it's explained in your textbook on page 213. You have to explain it in your um, on your assignment. All right, again, let me know if you have any questions. Feel free to email me or we'll go from there.